First of all, thank you for giving me the opportunity to talk here. And today I would like to talk about invariance of Plurigenera for foliations on surfaces, and this is a joint work with Paolo Cascini. So I'll start with an introduction. In what follows, X will be always a complex projective surface. And a foliation or holomorphic foliation on X will be a subbundle of the tangent bundle. And we require some more properties on TF. So it defines a short exact sequence. And we require that the quotient is locally free everywhere with a finite number of exceptions. So we write the quotient this way, where NF is a line bundle and EZ is an ideal sheaf, such that the support of Z is a finite set. And we call this set the singularities of our foliation. Okay, the dual of TF is called the canonical bundle of the foliation. And we say that a curve C is F invariant if it's tangent to the foliation. What does it mean? It means that the tangent bundle of C is parallel to the restriction of TF to C. Okay, so outside the singular locus, a foliation is the partition of a neighborhood into parallel curves. Let me just draw a small picture. So on X minus the singularities, F is just a partition of a neighborhood into parallel curves. And if this local partition comes from a global partition of X into compact curves, it means that our foliation comes from a fibration. So this is the first important example. Let's consider F, a fibration, which is a surjective morphism with connected fibers. Then F induces a foliation. And if all the fibers of F are reduced, we have a nice expression for the canonical bundle of F. So the canonical bundle of F is the relative canonical bundle of the fibration. And we can understand also a little bit better what the singular points are. Because, for instance, if we have F, a fiber, such that its support is singular, the singular point of the fiber is a singular point of the foliation. So we will have our singular fiber. This is a singular point for the induced foliation. In view of this equality, we can have an intuition of what the canonical bundle of the foliation, of a foliation is. We can think of it as something that, restricted to F-invariant curves, is just the canonical bundle of the curve. I want to give also an example. So here, all the F-invariant curves are compact curves. I want to give another example of a foliation such that none of its F-invariant curves is compact. And we can obtain it on the torus in dimension 2. Let's say that on C2, we can take a distribution of hyperplanes with lambda, for instance, non-rational. So this distribution of hyperplanes projects to the torus and gives something that, for instance, on the real model of the torus can be visually represented in this way. So a leaf is something which fills densely the torus, and so on. The next definition will not be very precise, but it will become very precise in the next section when I will describe what singularity we allow on the foliations. But let me make it anyway. So we have F, a foliation, and we say that the Kodaira dimension of F is the Kodaira dimension of its canonical bundle, which controls the order of growth of the global sections of the canonical bundle and its tensor powers. So I will also write the definition of Kodaira dimension. And there are two important properties or facts. The first one is that the Kodaira dimension can take the values -infinity, 0, 1, and 2. And the other one is that the Kodaira dimension is -infinity if and only if we never have global sections of the canonical bundle. So recently, Brunella and McQuillan completed a classification of foliations on surfaces. I'll say, okay, on the model, in the spirit of the classification of Enriques and Kodaira for surfaces. What does it mean? It means that foliations of Kodaira dimension -infinity, 0, and 1 are described. And the ones of dimension 2 are a big realm of foliations called of general type. Okay, the next step after classifying foliations on surfaces is trying to understand how foliations behave in families. So let me define what a family is. So we will always take families over the disk inside C is a family of foliations, and it's the data of, first of all, a smooth morphism, such that all the fibers are surfaces, projective surfaces. Then a foliation on these, so F foliation on the threefold X, which is tangent to pi. Being tangent to pi means that all the F invariant curves are contained in fibers of pi, and this implies or means that F defines a foliation Ft on Xt for all t. And third, we have some technical hypotheses that will be very clear when I will discuss the singularities of F. But for the moment, I will just leave it like that, in a box. But Brunella proved that for a family of foliations, we have invariance of the Kodaira dimension. Okay, so the next natural question is asking, what about the global sections of the canonical bundle? So I would like to discuss and answer this question. And so those dimensions is what we call the plurigenera. Of F. And I will give you the answer. The answer is given by the theorem. So the first remark is that by Brunella's result, we can treat the three cases separately. Kodaira dimension 0, 1, and 2. The case of Kodaira dimension minus infinity being already settled. So if the Kodaira dimension is 0, we have invariance for all m. For all m, the plurigenera of Ft do not depend on T. The case of Kodaira dimension 1 is a little bit more interesting. If the Kodaira dimension is 1, we have two cases. The first case is if Xt Ft is given by an elliptic fibration for all t. And in this case, we can find an integer which depends only on the foliation, such that starting from this, so I'm 0, starting from this integer, we have invariance. Okay. Sorry? Yes, yes, exactly. Okay. And we have an example where invariance fails for small values of m. So there exists XTFT, a family like before, such that the sections of the canonical bundle depend on T. And so for Kodaira dimension 1, in all the other cases, we have invariance for all m. And finally, when the Kodaira dimension of the foliations is 2, for all m big enough, the plurigenera do not depend on T. And again, we have an example of family of foliations of Kodaira dimension 2, where the sections of the dimension of the sections of the canonical bundle depends on T. Okay. Okay, I would like to spend a little bit of time on motivations. And for the motivations, I would like to talk about the interplay between two words. On one side, there's the word of birational geometry. And on the other side, there's foliations. So in one direction, in the last few years, a birational approach has been very useful for the study of foliations. And one example is, for instance, the classification by Brunella and McQuillan. And a birational approach means study the canonical bundle of F, the Kodaira dimension of F, the Zariski decomposition of the canonical bundle of F. On the other side, so when we have a fibration on a variety, we know some geometric information. It determines some geometric properties on the variety itself. And the same thing is true for foliations. So if we have a foliation on X, then we can deduce some geometric properties of X. And I probably should mention as well that there is a strategy for the proof of abundance conjecture, which is mainly based on foliations. But more precisely about this problem, I should mention the important theorem by Siu, and there is a proof also by Paun, saying that if we have a smooth morphism, then the plurigenera of the variety do not depend on T. This is what's known about as invariance of plurigenera. Okay. Okay. Now I can make everything more precise. And I would like to talk about the singularities we allow on our foliations. So we have a foliation F on X, and we consider a birational morphism. So F defines a foliation F on X tilde minus the exceptional locus of epsilon. And this foliation F can be extended in a unique way to an F tilde on X tilde. So now we are ready to define the singularities we want to consider on our foliations. We say that F has reduced singularities if whenever we consider a birational morphism, the difference between the canonical bundle of the foliation F tilde and the pullback of the canonical bundle of F is an effective divisor. Okay. Having reduced singularities or not changes the local phase of the foliation. Let me just draw a few examples. If we take X a smooth point, or I will use P, the foliation around P looks like that. We have here P somewhere. And so an example of reduced singularity so what I'm drawing is a schematic picture of the F-invariant curves around P. Whereas an example of non-reduced singularity is given by a foliation. So here we have P, a foliation where the F-invariant curves are lines through P. Okay, there are two important facts about F-invariant curves and reduced singularities. The first one holds for any foliation. So for any P, we have an F-invariant curve through P. But if F is reduced, the F-invariant curves through any point form a simple normal crossing curve. So, for instance, a simple consequence is that they are a finite number. Not like in this example, but in this example. There are at most two. Okay. I can use this. No. No. Sorry. Okay. But from the definition that is not visible anymore, from the definition we can deduce that if F is a reduced foliation, then the plurigenera are birational invariants. So for any birational morphism, we have an equality between the global sections. But most of all, what makes reduced singularity so important is a theorem by Seidenberg saying that if we have F, any foliation on a surface X, then there exists a resolution of singularities. So we can find a birational morphism such that F tilde, the foliation on X tilde is reduced. And in view of this proposition and of the theorem, we can make the following definition. So we have F, a foliation, and we say that the Kodaira dimension of F is the Kodaira dimension of the canonical bundle of F tilde, where F tilde is as in Seidenberg theorem. And I will just like to stress that passing to the resolution f tilde is really necessary. So in general, if f is non-reduced, it may happen that the Kodaira dimension of its canonical bundle is different from the Kodaira dimension of the resolution of singularities. Okay, I am also ready to give the precise definition of a family of foliations. So, as I said before, we need a smooth morphism whose fibers are projective surfaces. We need a foliation F on the threefold X, inducing a foliation on every fiber. And we impose something on the singularities of the foliations. So we require that the singularity of the foliation defined on the threefold meets every slice in a finite set exactly equal to the singularity of the restricted foliation. And we want also that the foliations Ft are all reduced. Okay. So, one remark about this definition. The third property is probably, in some sense, the most important one. Because the third property is what makes that the whole problem makes sense. So, it implies that we have a line bundle on X that restricted to any slice, any fiber, is the canonical bundle of the foliation restricted to the fiber. Okay. Okay, in the time that I have left, I would like to give you the example of a family of foliations induced by elliptic fibrations. such that the dimension of the canonical bundle of the foliation depends on the parameter. So for that, we will consider a curve of genus at least 2. And the line bundle on the curve, which is the sum of the canonical bundle and the difference of 2 points, where P and Q collide. So PT is different from QT when T is different, when T is non-zero, and P0 equals Q0. With L, so LT defines an elliptic fibration over C. This via Weierstrass model. Moreover, this elliptic fibration has just reduced fibers. And, oh yeah, so xt, okay. Whenever we have L on a curve such that the second tensor power of L and the third tensor power of L have sections, we can construct with those sections an elliptic fibration, putting in family the Weierstrass model. So let's say that we have S2 and S3 here, and we consider, I don't want to, something like that. So this gives the family. Pardon me. S2x, yeah. Yeah, absolutely, because it's, yeah. Thank you. So phi t has reduced fibers, and the relative canonical bundle of the fibration is the pullback of LT. And so we are done, because the H0 of LT is G if T is 0, and it's strictly less than G if T is not 0. Up. Okay. So I think I have 5 minutes of time to give a quick idea of what's used in the proof. And maybe I should be precise and say in the proofs, because each case has its own proof. So The first remark is that by Brunella's result, we can treat separately Kodaira dimension 0, 1, and 2. Another very important thing, so this is one. Another very important thing is that when the canonical bundle of F is pseudo-effective, we can consider its Zariski decomposition. And Brunella and McQuillan studied carefully the geometry of the negative part of the Zariski decomposition of the canonical bundle. And they proved, under some technical hypotheses, that the support of N is a disjoint union of Hirzebruch-Jung chains. So Ci is a chain of rational curve of self-intersection at most -2. And they are F invariant. So this is the first ingredient. And the second ingredient is the key lemma proved by Brunella that proved that for a family of foliations, we can find a divisor N on the threefold X such that restricted to H fiber, it gives the negative part in the Zariski decomposition of the canonical bundle of the foliation on the fiber. And N meets the fibers transversally. So for the Kodaira dimension 0, those ingredients more or less are sufficient to solve the problem. In Kodaira dimension 1, we have to use a little bit more the classification by Brunella and McQuillan, plus some extra work. And in Kodaira dimension 2, we use in a it's very important to use the Kawamata-Fivek vanishing theorem in order to achieve the result. And that's all. Thank you. Mm-hmm. Yeah, I don't know what I should interpret as a local version, but I mean the answer is easy, and it's certainly in our proof there is no interpretation of this kind. No, me neither. I'm sorry.